you all so much for coming and joining for the first of this series of 9 lectures about how our solar system is formed, which is just my favorite topic and the favorite topic of lots of friends. And so I want to start by just putting everything in perspective, which is to say, I want to show this timeline. So here's a timeline that starts at the right with us right now and moves to the left through the age of our universe. The Big Bang, the age of the universe, 13.787 billion years ago, plus or minus 20 million years. That means that by using a number of different ways to measure the age of the universe, a group of different scientists have come up with this idea that with 95% certainty, the age of the universe is 13.787 billion years, plus or minus 0.2, that is, 200 million years. And so about 100 seconds after the origin of the universe, the temperature was 1 billion degrees Kelvin. And 30 minutes later, the universe consisted of 72% helium, 72% hydrogen, 28% helium, and traces of lithium and beryllium. But our solar system starts so much later. So 4.5673 billion years ago were the first solids in our solar system. And by that time, stars had formed and grown and died over as many as 6 different generations. And those stars had made all the elements that we have in our solar system now. Our sun is probably about a 3rd generation star. And that's lucky, since hydrogen, helium, lithium, and beryllium is not enough to build the beauty of the Earth and everything that's around us. We need all the elements in order to build that. And those elements are formed by the generations of stars that predated. And so note that throughout, I'm going to try to show what science, throughout these lectures, I'm going to try to show what science thinks is the best explanation for what we see, and what is the data and the theory behind these ideas. And then look for citations at the bottom of the screen in gray font. These are some of the peer-reviewed journal articles with the primary information in them. And so here's the timeline we're going to use for our series of lectures. And today I'm going to talk about what is a star forming region, what is it made of, how do we know, what evidence do we have from our own solar system to know what it's made of and how it started. And I'm especially excited to show these lectures now because for me, the immensity of the timeline of our solar system and of our universe really are comforting. And these are distressing times that we're in, and looking out at the beauty of our universe and understanding where we came from, it seems very timely. All right, so here's that same timeline. Oh yes, the age of the first solids in our solar system. Here's that same timeline, 5 billion years worth of time. This is really the timeline that is going to be discussed over these 9 lectures. One of the problems we have in understanding planetary science and astronomy is the gigantic distances and the immense depths of time. So let's start by thinking about the notion of a billion. We really have no human intuition for a number this big, but this may help. Imagine a standard glass marble, just a little marble, just one in your hand. It covers 1/4 of a square inch of area. And if you pack it in a square grid with its neighbors, you could imagine each one taking up 1/4 square inch. Now imagine you're standing on an American football field with your marble. Put the marble in the exact corner of the field, and then start lining up marbles touching it, one after the other, all across the end zone back line. Keep lining them up. Then make another line in front of the first line. When you finish filling the entire field, including both end zones, you'll have used 33 million marbles. So you'd need 3 football fields full of marbles to make 1 billion. And those first solids in our solar system, little pebbles, effectively formed 4.5673 billion years ago. And now do you see this vertical orange line underneath the timeline? I just put an arrow pointing to it to make it more obvious. That's the span of time we're going to talk about today, just a few million years before and right up to the first solids forming in our solar system. And in this time period, I'll try to answer the questions: how do solar systems form, and how do we know? And what is the composition of our solar system? And what is the very beginning of planet formation? Because the next lecture, next Thursday, will be about building the planets. All right, the short answer is solar systems form from giant molecular clouds. This picture you see right here has generations of stars in it. This is an infrared image from NASA's Spitzer Space Telescope. In this star-forming region, which is called W5, the oldest stars can be seen as blue dots in the centers of the two cavities. And so I'm going to circle them with my cursor here. These are the blue dots in the centers of the cavities, the oldest ones. And then the clouds in the clouds of the gas and dust that make up the giant molecular cloud are in green, red, and white. And these are infrared colors. They're not literally the colors you see with your eyes. Younger stars rim the cavities, and some can be seen as little dots at the tips of these pillars of gas and dust, like the ones that I'm circling right here. These white areas are where the youngest stars are forming. W5, this region, spans an area of sky equivalent to 4 full moons, and it's 6,500 light years away. We would see it in the constellation of Cassiopeia. Note, though, that this amazing area is fairly dark in visible light. All the color is from infrared wavelengths, and more on that in a moment. Molecular clouds have masses on the order of 1 million times the mass of the sun. But stars form from the gravitational collapse of fragments of these giant molecular clouds. And the collapse, this is really key, the collapse is probably triggered by a shock, such as one from a supernova explosion. And if you remember this idea that the shock from an exploding star, a supernova explosion, might cause this cloud of gas and dust to start to collapse into a sun, this will become very relevant in the next lecture when we talk about some products of that supernova explosion. So this is the takeaway here. Solar systems form from giant molecular clouds. And the dust, so we've got the giant molecular clouds consist of about 95% hydrogen gas, about 4% helium gas, and about 1% dust. And that dust is partly organic molecules and partly all the other elements besides hydrogen and helium, which is kind of amazing if you think about the fact that all our bodies and our planet and everything around us is mainly made from elements other than hydrogen and helium. But hydrogen and helium is what the solar system predominantly starts out as. Now the density, this is rho, that means density, of a giant molecular cloud is between 100 and 10 to the 6th molecular molecules per cubic centimeter. That might seem like a lot of molecules per cubic centimeter. It did to me when I first read it. But by comparison, air at sea level has a density of almost 10 to the 20th molecules per cubic centimeter. And so this is very, very few molecules by comparison. Let's look for a moment, I love this picture, at the center of our own galaxy, the center of the Milky Way. This image is made from X-rays, while the previous one was made from infrared radiation. So this is also an area where we mostly cannot see it with our eyes. It looks dark, but look how bright it looks in X-rays. It's really pretty amazing. So first, look at this feature called Sagittarius B over here on the left. This is a giant molecular cloud where new stars are forming. And amazingly, astronomers trying to identify the composition of the dust that comes along with the hydrogen and helium, that dust, found the organic molecule ethyl formate. Ethyl formate is the exact molecule that gives raspberries their smell and rum its flavor. And so Tanya Harrison worked with us at ASU to make center of the galaxy lip balm with that flavoring, which I still think is completely hilarious, and it's one of our favorite kinds of swag. So that might be the only nice smelling part of the giant molecular clouds we've found so far. Now there's another amazing feature in this image, which is Sagittarius A star. This is the supermassive black hole at the center of our galaxy. Data from Chandra and other X-ray telescopes suggests that giant X-ray flares from this black hole occurred about 50 and about 300 years before this image. So, you know, within human memory. But luckily, it's 25,640 light years away. And recall, I'm not really sure who's on the call, so forgive me, I'm going to speak at many different levels, but recall that a light year is how far the distance that light travels in a full year. And so we are entirely safe from this scary supergiant black hole. So let's see, let's have a brief, what I'm going to call a public service announcement. Let's talk about the electromagnetic spectrum. Here's the spectrum up here at the top. From the tiniest wavelengths, the highest frequency things, which are gamma rays, down through X-rays, the ultraviolet. Here's the visible spectrum of light right here, what we can actually see with our eyes. For all the rest of this, we have to rely on technology we've invented to measure it. Infrared, microwave, radio waves, and finally very long radio waves. And I want to point out that X-rays are what that last image is made of. They're made of detections of X-rays showing the center of our galaxy. And the one before that, the one that was showing that very first giant molecular cloud, that is in the infrared. So a little public service announcement about the electromagnetic spectrum. Now, what happens to the collapsing giant molecular cloud region? The collapsing molecular cloud falls inward and becomes what's called a protoplanetary disk. This is a protoplanetary disk, or rather, really, it's an artist's drawing of a protoplanetary disk. This is not a picture, but I'm going to show you one in a minute, an actual picture. The center of this spinning disk of gas and dust becomes the protostar, which eventually turns on its nuclear fusion and becomes a star. So the protostar is not yet undergoing nuclear processes, and the disk all around the star is the birthplace of the planets. And although we can't look back in time to see the disk that formed our solar system, we can use telescopes to look out at young stars elsewhere in the galaxy and see their disks. And here's an amazing thing we've come to know in just the last decade or so because of all of the intense study of exoplanets, that is, planets around stars that are not our own. Almost every single star is born with planets. So next time you look up at the night sky, think of that. Every star up there probably has planets orbiting it. That just blows my mind. I think it is one of the huge advances in human knowledge that we've had in the last decade. So maybe you're asking, and I asked, why are protoplanetary disks flat? If it starts with a great big ball of gas and dust, why does it end up flat? Well, why are solar systems shaped like disks? Here's the region of the giant molecular cloud that is collapsing under its own gravity and forming that protostar in the middle. It's spinning, which you can see I've drawn its axis of spin that goes right through it, just like the north and south pole of the Earth, but this is a huge cloud of dust and gas spinning around its pole. Now all the gas and dust in the spinning ball feels both the pull of gravity toward the center of the ball and also centrifugal force that would move it further away from the center of the ball, that would fling it outward. Famously, people always say, imagine that you're holding hands and you're ice skating and you're the end of the whip, you know, that you're feeling the centrifugal force. The material at the equator, where I've drawn those arrows, and in fact, all the way around the equator, is moving the fastest, and it feels the most centrifugal force. The disk develops in a plane perpendicular to this axis of rotation. It develops in the plane of the equator where the centrifugal force can balance the infall. And so just like that same kind of ice skating analogy, when a spinning ice skater pulls his arms in and spins faster, the infall of material to the center of this spinning ball of gas and dust makes the whole cloud spin faster and makes it spread out even faster. So that is why the disk ends up, that's why the ball of dust and gas ends up as a disk. Now let's look at some real ones that we actually can see with telescopes. So first let's parse this title. This protostar, which is right here in the middle, is called HH30. And it is 450 light years away in the constellation Taurus. And this is a jet that's being sent out of its North Pole, actually, or its South Pole. I'm not actually sure which way it's spinning. And it is called, it's called a T-Tauri jet. T-Tauri itself is a variable star about 460 light years away, also seen through the constellation Taurus. And it's the first identified example of these active jets in young stars. And so all the jets are named after T-Tauri now. So this is the protostar HH30. It's a baby star, and it's making this gigantic, crazy jet of heat and matter called T-Tauri jet. Now, what does this have to do with what I was just showing you? This right here, you're seeing edge on the protoplanetary disk. This is the disk of gas and dust that has settled down into a disk with the baby star right in the middle, and it is in fact getting ready to make planets. And these outburst winds, though, are incredibly energetic, and the movement of the matter in them can be as fast as 300 kilometers per second. Observed outbursts have developed over 1 to 20 years, and then they decayed over 55 to 100 years. So they burst out and then they fall back after quite a number of years. And when I first learned this, I was pretty amazed because in my mind, at least, the stars and everything that we saw outside of our solar system were more or less fixed. I didn't really expect that there'd be processes we could watch on a human lifetime. Imagine what it's like for little planets that might be forming in that disk to have these kinds of super energetic jets happening. It's a pretty high energy and rather dangerous kind of place to be living. Now, let's find out what happens inside these stars. So this is a kind of a public service announcement about nucleosynthesis in our sun. In case you haven't reviewed this recently, or if this is a new idea to you, this is what happens when nuclear processes turn on in a star, when it stops just being a ball of hot gas and dust and it actually starts shining like a star. And so while it's just forming in the disk and it's still sending out those crazy jets, the young star has not yet turned on. But around the time that planets start to form, the star turns on. And this is what's happening inside the star. First, 2 hydrogen atoms, which are here on the left in this equation, and here in the picture, 2 hydrogen atoms combine. They're really just 2 protons. They fuse and they create a deuterium. Oops, go back. They create a deuterium, which is this guy right here, and this guy right here in the picture, plus a positron and a neutrino. And that happens twice. You can see the one on the right. And then the next thing that happens is this. 1 deuterium and a hydrogen fuse, and they give off a helium-3 and a gamma ray. And that happens twice, on the left and on the right. And then, finally, 2 helium-3s combine to make a helium-4, and they give off 2 protons. That is the process by which helium is made in stars, and it is the process that creates light for us on Earth. It's the gamma rays that give us light. So thinking back through this little process I was just describing, this is actually the process by which stars take hydrogen and produce helium and light. And the gamma rays that are created here in step 2, these gamma rays, once a gamma ray is made, it begins colliding with other particles inside of the star. And collisions and then re-emissions of that gamma ray take 1,000,000 years for the gamma ray to exit the sun. So once it's made, that gamma ray bounces around for 1,000,000 years between the time it leaves. And through all those bounces, it loses energy, and it's been reduced to the visible spectrum. I don't know if you remember that in the last public service announcement, the left-hand most part of the electromagnetic spectrum was gamma rays. And by the time those gamma rays have bounced around for 1,000,000 years, they're in the visible spectrum and we can see them. And here's another amazing thing. Because energy and mass are equivalent, to shine, the sun must lose mass. A helium nucleus, the product at the end of this, is 0.7% less massive than the 4 protons that went into making it. Converting a proton to a neutron releases energy and uses mass. 5 million tons of mass are converted to energy every second in our sun. So someday our sun will run out of hydrogen to burn, but that is another story. So back to the disk. This is a schematic of what a disk looks like from the side. And so if you look on the left, that's our young star. And if you look way on the right, this is the edge of the disk. So it's just a section of one part of the disk. Out here, you can see these blue arrows. There's inflow to the star from the remnants of the molecular cloud. Really, this star is hollowing out a kind of a cavity in the molecular cloud, a small cavity. The inflow to the star is about 10 to the -5th star masses per year. And then in the middle of the disk here, there's a zone that's really ideal for planets to accrete, that is, planets to clump together. And you can see down here in the red bar, between 1 and 8 astronomical units out. Recall that an astronomical unit is the distance from the sun to the Earth. And so that's, here we're talking about about the distance of the Earth out to about 8 times the distance of the Earth. Temperatures are between 700 Celsius, way too hot for us humans, but not bad for making a planet, down to as cold as -200 C, where a lot of ices would occur. Now think about that for a minute. this really aligns beautifully with our simplistic human way of thinking that things that condense at high temperatures, like rocky planets, might condense nearer the sun, and things that are filled with ice or gas, or things that would condense at low temperatures, would condense far away from the sun. And that's what we see in our solar system. Turns out that's not seen in every solar system. And we'll talk about this more, but planets can migrate around and really confuse this story. But that's really how it starts out. And then very close to the sun, there's really a lot of madness. First of all, there's magnetic field from the spinning disk. The dust and the charged particles in the spinning disk make their own magnetic field, and their lines are shown here. The sun has its own magnetic field, which interferes with the disk magnetic field, and it curves the inflow of mass into the sun, and it shoots other mass back out into the disk in something called the X-wind. And so you might be gathering that this is a pretty violent and relatively unfriendly place for planets to be born. And yet, the primitive, here it is, the primitive material from the beginning of the solar system. This is a thin section, or sorry, no, it's a slice of a hand sample of a piece of the Allende chondritic meteorite. This chondritic is, describes a meteorite, something that fell from space, that contains little round pieces like this one that are called chondrules. And those are thought to be little glassy, almost bubbles of material that formed in the early solar system. So that's, it's kind of shorthand for a meteorite that we don't think ever melted. We don't think it was ever heated to melting. We think maybe it had fluids flux through it, but it is really the primitive material that first condensed out of that gas and dust disk. And this guy in the red ring down here is something called a calcium aluminum inclusion. And that is the material that's used to date the first solids in the solar system. These calcium aluminum inclusions, in fact, in this very kind of meteorite, Allende, many, many, many tons of it fell in one day, all from the same parent body, are the oldest calcium aluminum inclusions, the oldest objects in the solar system that humans have yet found. And so this guy right here might date to that 4.567 billion years ago age that we talked about in the beginning. And so how do we know that the composition of primitive meteorites really is the composition of the beginning of our solar system? Well, early on, Ringwood in 1979, and then others who have followed him, graphed the abundance of elements in the sun, that's the vertical axis here, the abundance of elements in the sun, versus the abundance of elements in these chondritic, these primitive meteorites. And you can see here are red dots, each one standing for a different element in our periodic table. And they're not all right on that line, and there are various stories about that, which I'm not going to talk about. But really what you see here is more or less a one-to-one relationship between what's in those meteorites and what's in the sun. And because the sun is by far the largest mass of our solar system, it represents more or less the bulk composition that we started with. And so that's how we know, another way we know that these chondritic meteorites are very primitive and they represent that first material. Another way that we know is here's a solar spectrum. You take sunlight and you split it with a prism, and you line up all the lines of the spectrum as if you were reading lines in a book. And you see these black lines, you see these black lines that interrupt the spectrum. Those are places where atoms are absorbing that particular wavelength of energy. So we don't see it with our eye, it shows up black. And we can match the exact atoms with the wavelengths that they absorb and know the composition of our sun. And so that's how that data comes to be. Now, finally, it's very interesting to know that more than just gas and molecules of dust formed our solar system. There are also little tiny grains. These are found in meteorites now, pre-solar grains, little tiny bits of grains that predate our sun. And even today, interstellar grains fall onto the Earth, and they're found in Antarctica. So these are mineral grains from outside of our solar system. And identified phases of these little tiny grains include diamond, silicon carbide, graphite, even sapphire, and even silicates, little bits of rock. And they can be identified as not coming from our solar system because of the isotopes. The weights of each of their different elements are much more widely spread than what we find in our solar system. So that's kind of amazing to think that even now we're being sprinkled by tiny, tiny grains of minerals that come from outside our solar system. And so here's the summary. Here's back to our timeline, and here's the summary. We started with this idea that giant molecular clouds form solar systems. They are on the order of 100 light years across, about 10 to the 20th centimeters. And we went through the idea of a disk with the giant molecular cloud, flattens down into a spinning disk, a complicated disk that planets form in that we'll talk about next time, of let's say about 200 astronomical units or 10 to the 15th centimeters. And finally, that oldest material, the thing that actually creates that date of 4.567, some of the first pebbles that formed here is this calcium aluminum inclusion in a meteorite, and the calcium aluminum inclusion itself is only about a centimeter across. And so that concludes our rapid lecture number 1 on how solar systems are formed.